Okay, so as we get started here, the biggest thing when we're talking about work, this overhead's kind of being a little slow with this computer. I don't know what the issue is. Let's try this again. Okay, oh, there we go. Finally getting, yes, we're getting a little closer here. All right, so what is the main idea when we're talking about that of work being done? There has to be a what and a what. There must be an applied force, and it has to be an object on applied force on that object. Yes, yes, and there has to be movement being done. Okay, or specific distance. That's right, and that's written in your formula. That work equals force times distance, and that's why one of the things you could say. Did anyone ever watch Little House on the Prairie, or has even ever heard of that show? So it never really was mom and dad, was it? It was, what were the, you call them pronouns? My English isn't the bestest, so say that again. Ma and pa, okay? So that's why you can say, don't mess with mom because she's a force. Because what does force equal? Acceleration. So force, so ma is a force. Ma is a force to be reckoned with. Don't mess with ma, right? Wouldn't you agree? Don't mess with ma. Okay. So, regardless, okay. Some of you have seen that physics shirt that I've worn, where it says,
Are you on the
yeah,
bus?
that says that on the back. Yes. That's one of the things that I had a chemistry professor that would ask. His way of asking if you understand is said, "Are you on the bus?" So that's just one of the things that I little kind of quirks, or if you want to call it that, that kind of maybe carries forward with one of the things that I had learned from himself. And that shirt goes on to talk about this here, if this will, man, this really just does not want to cooperate. Okay. Um, the idea that we just said you don't want to mess with ma because she's a force. Okay? Yeah. Force equals mass times acceleration, right? And we know that what does work equal? Force times distance. Okay? So if we substitute equal values, then we know what force equals, mass times acceleration, right? So does work ever make you angry? This is another way you can write that. Work equals mad. We told a physics funny. It's a good one, isn't it? Right. That's a good one. So if two things you ever learned from this class, one, don't mess with mom because she's a force. Two, sometimes work can make you angry. See, we're learning something every day. It doesn't even have to be science related, although this probably reminds you of, but anyway. So moving forward then. All right, we won't have a whole lot to get through today, okay? Like what we said yesterday, you're lifting these up. Yes, you're applying a force on those books, okay? But the books aren't moving, the backpack is, okay? Because as you have that strapped on your back, again, you're not doing any work on the books because, as we we said, those have to be something that you're actually moving. So in some of these cases, what we see here as well, the idea that when work is done, it's a transfer of energy, and that's also Newton's third law, as we all know, that for every action, you got that equal and opposite reaction. So when this work is being done, you're transferring that. That also takes place in different types of energy: electrical energy, potential energy, kinetic energy, chemical energy. Any one of those. For those of you who go into higher order life science classes, like not so much zoology, but a little bit of anatomy and physiology, and even when you get into that in college, it's the breakdown of certain types of molecules in our cells. That's chemical energy, where many different biological processes are fulfilled or carried out, and that is an example of chemical energy. Okay? Next semester, we get into that of the chemical energy as well, dealing with the periodic table, because one of the forces that you had learned was the strong, the weak, the electromagnetic, that keeps electrons in orbit. Then the fourth one, that's the weakest, is that of gravity, even though we call it the weak force, but gravity is the weakest of all four of those forces. Okay. So this will be the last one that we see that we'll be working on today. Okay. And then as you can see on the bottom, that was the new formula you put on your sheet on Wednesday. In a few minutes, we'll get back to going back to that video that we started yesterday. Has anyone ever worked with rivets before in here? To me, they've always been kind of a, sometimes they work, sometimes they don't, but no one here ever has. Okay. Well, really what it is, just picture a nail, or I think I've got, for instance, one of these needles. Yes, like this here. Okay. When you look at a rivet, I don't want to say that too much. You can't think I'm a frog. Rivet, 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 rivet. I can't jump as far as a frog. Okay. You said throw it up, so I did. Okay. This is what a rivet would actually look like. And what you do is when you put that through what you're trying to attach, this is sticking through this end. And I don't know if it's I think it's called an emasculator gun. I think that's the technical term. And what that does is it grabs this and starts pulling. And what that does is it causes this to flatten out. In a similar sense, I've never had much luck with, have you ever heard of butterfly hex nuts? Does some of you people who maybe work with hardware, yes, no? Okay. Well, we won't go into that because I don't want to throw a whole lot of technical terms and confuse people, but okay. So regardless, the reason I mentioned that is that video yesterday talking about those two panels that are hooked together with rivets. If you really wanted that to be strong, you'd probably put another beam or piece of steel in the middle, and that would reinforce that. Because what they did is they took that bowling ball and they released that, with the rivets, it was maybe what? It was one or no more than 5, and that had torn itself apart. Well, with that tape, they said it was 20 times. Okay, that doesn't necessarily mean it's 20 times as strong. What it's saying is that the rivets don't hold those two, two surfaces together as efficiently as what that tape does. Okay. So with that, we will continue with, I can't remember what this was called, not World's Strongest. I think that had something to do with it, but I would certainly think the application for hydraulics is going to be a lot more than what you would think. I can't imagine that, like, the first automobiles that were made in mass production came out of Michigan. Do we know, for instance, what type of automaker that was? Henry Ford. Okay. And what type of automobiles? He made the Model A, but not as well known as the Model T. Okay. But why might some people have a hard problem driving something like that down the road, especially if you have to turn a corner? It didn't have what type of steering? Didn't have power steering. You actually had to muscle that yourself. Now you can just take a finger and turn the wheel just like this, and of course the wheels will turn like that. And what it is, it's a hydraulic pump that turns those tie rods. Okay? And that's what makes hydraulics such an efficient way of doing work. Another one is, if you ever heard of a braking system, you may have to replace a blank cylinder. Yeah, it's the master cylinder, and that's what pumps the fluid to your disc brakes. Okay, and notice the harder you press, the harder it's going to push that brake pad up against the drum. Okay, so those are applications of hydraulic fluid that's in your vehicle. It's just something that you never really think about, and I really don't either, because chances are, if your brakes are squealing or if you can't turn your vehicle, we dial up 534-5684. Mr. Tim, that's right, and he'll fix it. That's right. Well, you can call AAA, but they still have to get it to the repair shop. So we will pick up with this information then on Monday, and we'll start some problem-solving activities then as well. All right.